Good morning. First of all, let me thank Charles Hungr for his kind invitation to contribute in this nice symposium. I will try to share with you my experience on the fast flow-like landslides that periodically occur in the country where I live, involving non-plastic granular soils and sometimes causing casualties and severe inconveniences. A careful survey of the most recent events in the world indicates that the number of casualties due to non-coseismic events in the time interval 2004-2016 has been around 56,000, thus much more than 4,000 per year. The strongest impact has been recorded in Central and Eastern Asia and in Central America. Italy fights for the first place in Europe. Flow-like landslides are probably the most destructive phenomena due to their high displacement rate and often big volumes, thus high kinetic energy. Italy again, and the region where I live, Campania, is a leader for the variety of flow-like movements which involve either granular, either plastic fine-grained soils. This slide, which reports the number of casualties due to landslides in Italy in the last century, about 11,000 victims, shows that the most severe events, but the violent landslides, occurred just in Campania. All landslides indicated with a red arrow are flow-like movements in pyroclastic soils. Such phenomena are the topic of this presentation. This figure shows the location of landslides occurred in the last 2 centuries in pyroclastic soils in Campania. In the figure, you can notice the position of Naples and of 2 active volcanic centers, the Phlegrean fields and the well-known Vesuvius, both very close to Naples. The 2 framed localities, Gragnano and Sarno, are the subject of the following 3 slides. This is the first site, Gragnano, which is famous for the production of pasta. In the figure is indicated the location of landslides occurred in the 18th century, in the 19th century, and in 20th one. The figure then suggests the repeatability of these events, some of which caused several casualties. This impressive slide in turn shows the flows, around 40, that occurred on May 5, 1998, all around the Pizzo d'Alvano mountain, causing 159 casualties and strong destruction in 4 villages located at the foot of the mountain, which are framed in the figure. This is a frontal view of some of those landslides. It may be useful now to give a look to the typical features of this phenomena. This figure, taken from a book of Branston and Trier, depicts the idealized velocity profile, which can be seen also as the displacement profile of a flow-like landslide. It is shown both in plan and in a vertical section. The figure suggests that the soil moves as a liquid mass, displaying a classic parabolic velocity profile. Being seen as a fluid, no shear stresses are indicated at boundaries. However, remembering that such a profile represents the behavior of soil mass, the figure suggests the development of high shear strains. An intriguing point is now how justifying at the same time a nil or very low shear resistance at the boundaries of the moving mass and high shear strains within the same soil body. The only explanation should be a drop of the effective stresses, which affect both the frictional component of shear strength and the shear stiffness. Such a drop in effective stress might be explained as an effect of a loss of contacts between particles. In a saturated soil, this is possibly due to the building up of high positive excess pore pressures. The drop in strength causes an imbalance between driving forces due to the self-weight of the soil and the decreasing resistance forces. A major consequence is mass acceleration with rapid attainment of high velocities. This is well demonstrated in this figure taken from a paper by Fell et al., which shows the typical velocities of different types of flow-like landslides. With the exception of earth flows in clayey soils, which can dissipate some energy due to viscous interparticle forces, in all other cases, the velocity reaches values of meters per second. Now it is time to give a look at the nature of the soils that are object of this talk and at the features of landslides that occur in such deposits. The soils that fill the plain around Naples and mantle the mountains around are a result of the activity of three distinctive volcanic centers, being volcanic ashes deposited by surges and by pyroclastic flows in areas surrounding the volcano, and by winds, the so-called ashfall or tephra, deposited even 100 kilometers far from the vent. The last eruption of Vesuvius occurred in 1944, during the Second World War. The mechanisms of ashfall sedimentation, adding new fresh layers in the pyroclastic sequence, are well evident from these photos. This picture provides a global schematic information about the nature of outcrops in Campania. We can identify three main geomorphological contexts. A volcanic context, those areas which surround the volcanic centers of Rocca Monfina in the northern part of the region, Phlegrean fields to west to Naples, and of Vesuvius to east. A carbonatic context, green in the figure, a terrigenous context that mostly consists of stiff clays and of flysch deposits, which is brown in the figure. The volcanic context consists of lava and tuff, mantled by unsorted, unsaturated cohesionless, non-plastic volcanic ashes deposited by surges and by pyroclastic flows. A vast part of both the carbonatic and the terrigenous context is mantled by ashfall deposited by winds having a prevailing west-east direction, as shown in this figure. This slide shows the grain size envelope of the volcanic ashes deposited by pyroclastic flows. As shown, the curves fall in the domain comprised between silty sand and gravelly sand. Plasticity is nil, and the void ratio is quite high, ranging between 1.1 and 1.6, corresponding to a porosity generally less than 60%. Similar data for the volcanic ashes mantling the carbonatic and the terrigenous contexts are shown in this figure that suggests their great homogeneity all over the region. Interestingly, the deposition conditions led to a higher void ratio than in the volcanic context. It is comprised between 1.8 and 2.8, which means a porosity with values exceeding 70%. Such high values of the body ratio reflect an open fabric. This figure has been obtained through the scanning electron microscope. The photo shows some sandy particles covered by a silty dust and separated by macropores. Silty bridges, however, establish some weak connections between sandy particles. Now it is time to give a look to the landslides that occur in these soils. Experience shows that rainfall is by far the primary cause of slope failure. Since these soils are unsaturated, failure is always due to a drop in suction, thus in the apparent cohesion, caused by the increase in water content. Another significant characteristic of these events is that generally they keep the features of flows. Referring to the advanced classification proposed by Hungr et al., these landslides are debris avalanches, debris flows, and flow slides. Debris avalanche is a very rapid to extremely rapid shallow flow of partially or fully saturated debris on a steep slope without confinement in an established channel, while debris flow is a very rapid to extremely rapid surging flow of saturated debris in a steep channel. Thus, a specific characteristic of debris flows is channelizing. Another typical feature of this phenomena is their strong entrainment capability of material and water along their path. This figure helps, I believe, in well capturing the types of phenomena at hand and the differences between them. This slide shows some recent examples of debris avalanches in the volcanic context, which fortunately no severe consequences. An example of debris flow in the carbonatic context is shown in this figure. As you can see, it was characterized by the confluence of three distinct debris flows, every one being fed by different sources. A big soil mass then reached the village of Quindici, located just at the foot of the mountain, killing 11 people. Based on experience, some authors outline that a very high percentage of the total number of debris avalanches and debris flows are the consequence of small slumps, just where small mountain roads cut the pyroclastic covers, shortly turning into big flow-line landslides. The upper figure shows two large debris avalanches originating from a cut, which is typically only 1 meter or 2 high. Another nice example of the mechanisms of landslide initiation is the debris avalanche shown in the lower figure, which was triggered by a very small slide fallen from a calcareous cliff. The same effect may be due to failure of earth fields, as in the case of these mountain roads. The third class of landslides is flow slide. According to Hungr et al., sand, silt, debris flow slides are very rapid to extremely rapid flows of sorted or unsorted saturated granular material on moderate slopes, involving excess pore pressures or liquefaction of material originating from the landslide source. The material may range from loose sand to loose debris, loess and silt. Usually originates as a multiple retrogressive failure. Therefore, an important distinct feature of flow slides is the small angle of the slope where they occur, and the fact that they are always characterized by the building up of excess pore pressures. This is an example of flow slide in the TERRIGENOUS context where clay soils outcrop and the slope angles are thus more gentle than in the volcanic and in carbonatic contexts. In these cases, flow slides triggering may be due to a mechanism of undrained progressive failure originating, for example, from the toe of an earth field, as shown before, or in zones that are characterized by an even little bit change in the slope angle. An example of liquefied flow slide is shown in this figure. Both the capability to entrain large blocks within a very gentle creek located at the foot of the mountain, as in the lower figure on the left, and displaced mud left on the walls of buildings, as in the right figure, suggest a complete soil liquefaction. This figure provides a synthetic framework about the characteristics of flow-like landslides in volcanic ashes in Campania. It summarizes a rich dataset about depth and angle of failed slopes. The data have been subdivided per context. They clearly show that the landslide in the volcanic context, lower figure violet color, occur on steep slopes with angles ranging, say, from 30 to 60 degrees. While the depths are very small, typically 1 meter or less. In the terrigenous context, yellow in the figure, failed slopes present the smallest angles, with values generally less than 20 degrees. In these cases, the landslide depth may reach 2.5 meters. An intermediate situation may be recognized in the carbonatic context, green color, where the angle of failed slopes ranges between 30 and 45 degrees. The depth of landslides is within 3 meters. Further interesting data concern the runout or travel distance. This figure reports the slope 8h and the distance L covered by all examined landslides. As it is well known, the ratio h over L represents the so-called reach angle, which is an indication of mass mobility. In the terrigenous context, the landslide height is of course quite small, thus the travel distance should be quite short due to the smaller slope angle. However, as shown in this figure, the runout that reaches 400–500 meters is comparable to that of landslides in the volcanic context, where failed slopes are the steepest one. As a consequence, in the terrigenous context, the reach angle is only 10 to 20 degrees, while it is 40 to 55 degrees in the volcanic context, where the landslide mobility is then much less. Finally, in the carbonatic context, the slope height may reach 1,000 meters and the runout 4,000 meters, leading to a reach angle as low as 10 to 15 degrees. In these areas, the risk is very high. Now, just a short summary on soil and landslides features. The pyroclastic soils present in the volcanic context were deposited by pyroclastic flows of surges. Their volume ratio is generally less than 1.6. The landslides in these deposits are typically debris avalanches and take place on steep slopes having angles comprised between 30 and 60 degrees. The runout is less than 300 meters and the reach angle ranges between 40 and 55 degrees. The carbonatic context is mantled by ashfalls with a void ratio higher than 1.8 up to 2.8. In this context, the landslides are debris avalanches and debris flows taking place on slopes with angles comprised between 30 and 45 degrees, which show clear signs of liquefaction. The runout may reach 4 kilometers and the reach angle is less than 20 degrees. The soils in the terrigenous context are ashfall too. Flow slides are usual slope movements that take place on slopes with angles even much less than 30 degrees. The travel distance may attain 400 meters. The reach angle is 10 to 20 degrees. Some data on the mechanical soil behavior can now help us in the interpretation of landslides mechanisms in the different contexts. This figure shows the results of some undrained triaxial tests carried out on undisturbed samples taken from both the volcanic and the carbonatic context. As shown, they present similar shear strength parameters, namely nil effective cohesion and a friction angle equal or a little bit higher than 35 degrees. The role of the void ratio on the mechanical response is, however, different and well evident. In fact, in the first case, volcanic context, the soil response is ductile, while in the second case, carbonatic context, it is brittle. Further interesting data are displayed by this figure, which shows the results of undrained triaxial tests after isotropic or anisotropic consolidation, carried out on specimens reconstituted at different void ratios within the typical range of values that characterizes ashfall. As already highlighted, all tests show a highly unstable soil behavior. An additional and clear information is that the peak strength is attained well below the steady-state line SSL and is followed by a strong drop in shear strength that leads the shear stress to attain the steady-state line under a very low mean effective stress that indicates the occurrence of soil liquefaction. The area between the envelope of undrained peaks of specimens having the same initial void ratio and the steady-state line SSL is the well-known instability region. As shown in the figure on the right that reports the results of tests on specimens anisotropically consolidated within the instability region, any even minor stress change under undrained conditions can lead to a fast and strong loss of strength. This figure shows the instability lines of specimens characterized by different void ratios. As higher is the initial void ratio, as lower the instability line. The mobilized friction angle of specimens having a void ratio in the region values between 1.8 and 2, namely typical values in the carbonatic and the interregional context, is less than 30 degrees, a value that is much less than the critical friction angle. This data, of course, shed light on the behavior of tephra that mantles wide areas in the carbonatic and terrigenous contexts. Finally, this is the compression plane of volcanic ashes obtained through a number of drained and undrained triaxial tests. You can recognize both the isotropic compression line ICL and the steady-state line SSL. The gray areas in the same plane show the range of values of the void ratio of samples taken from both the volcanic and the carbonatic context as a function of the presumed in situ mean effective stress after full soil saturation. As shown, the range of values in the volcanic context is located well below the steady-state line, while the range of values of ashfalls is above that line. This, of course, is consistent with the results of triaxial tests shown before. All previous data allow to propose a mechanical interpretation of the landslides at end. Due to the small depth of the pyroclastic covers, a first consideration is that the model of the infinite slope is suitable for simple analysis. Moreover, considering that rainwater infiltration is by far the first case of failure, and accounting for the range of values of the friction angle, the model of the infinite slope allows to easily calculate the apparent mobilized cohesion at failure. The results of this simple analysis are reported in the next slide. The figure suggests that in the volcanic context, where landslides generally occur on slopes with angles higher than 35 degrees and depth less than 1.5 meters, the mobilized cohesion at failure ranges between 1 and 6 kilopascal as a function of slope angle and soil depth. These values can be justified by suction values up to 11 kilopascal, as from the results of TRIAXIAL tests on unsaturated spacement not reported in this presentation. Therefore, slope failure involves a still unsaturated material. This might justify the quite high reach angle of these landslides. In contrast, in the TERRIGENOUS context, where the slope angle is always less than the friction angle, the mobilized cohesion at failure is nil. This suggests that failure occurs after full saturation, and possibly formation of an aquitard favored by the nature of the bedrock, which generally consists of low permeability fine-grained soils. Moreover, accounting for the data discussed before, failure might take place in the stability zone, thus giving rise to liquefaction. This can justify the low reach angle of flow slides occurring in this context. Finally, intermediate situations characterize the carbonatic context. There, the mobilized cohesion is, however, very small, suggesting a high or full saturation degree at failure. This indicates that in many cases, liquefaction is a likely phenomenon as well. As shown before, it might be due to impacts or to mechanisms of undrained progressive downslope failure. A number of experiments or small-scale physical models have been carried out in order to check some of previous hypotheses about landslide mechanisms. The experiments were carried out on slopes of reconstituted soil having a length of 1.2 meters and a depth of 10 centimeters, resting on an impervious base and constrained by a fixed pervious downslope boundary. A number of sensors were installed, including an optical fiber aimed at measurement of the strain distribution in the slope direction. This figure shows the equipment and the sensors used for monitoring. This slide reports some results of an experiment conducted on a model slope having a porosity of 70%, an angle of 40 degrees, and a void ratio of 2.3. The slope was subjected to artificial rainfall. As shown in the plot on the left, soil suction, which initially ranges between 60 and 70 kilopascal, rapidly decreases as a result of wetting. The effects of wetting are displayed first by the response of the tensiometers installed at mid-height in the layer, then by that of the deepest ones installed at the base of the slope. The figure on the right shows vertical displacement of the ground surface, which increase as the water content increases and suction decreases. Failure occurs after full soil saturation. This figure shows the records of positive pore pressures measured by 3 sensors installed at the base of the layer. the pore pressures start to grow 1 to 2 minutes before failure. This occurs suddenly and is immediately followed by a jump in pore pressures, which are magnified in the figure on the right as a result of process of spontaneous liquefaction justified by the high void ratio of the soil. Interestingly, based on measured pore pressures, we have calculated an upward hydraulic gradient of 0.5, which coincides with the critical hydraulic gradient, thus indicating the occurrence of a quick condition due to complete vanishing of effective stresses, a mechanism that can be recognized as soil fluidization. The second example concerns an experiment aimed at reproducing downslope progressive failure. In this case, the slope consists of two parts. The uppermost one, 40 centimeters long, has an angle of 42 degrees. The lowest part, 1 meter 50 long, presents an angle of 38 degrees. The void ratio of the soil is 2. In such a case, 2, failure was induced by artificial rainfall. This figure shows the results of monitoring with an optical fiber that highlights a mechanism of downward compression at different times in the pre-failure stage. In turn, the figures on the right show the rate of displacement at 5 monitored points along the slope axis and the pore pressure measured at 6 points. Even though the differences in displacement rate do not appear so evident from point to point, the first figure confirms a progressive downslope movement, while the other one, the lowermost in the figure, highlights the sudden building up of excess pore pressures. Now, some conclusive remarks appear useful. First, the cause of landslides in these unsaturated deposits is the decrease in the apparent cohesion due to rainwater infiltration. In the volcanic context, where the soil presents void ratios less than 1.6, slope movements are mainly debris avalanches on steep slopes with quite a high ridge angle. Failure should occur before full saturation. Liquefaction is unlikely, also because of the ductile undrained soil response in saturated conditions. In the heterogeneous context, typical slope movements are flow slides with a low ridge angle, thus a high mobility. Failure occurs after full soil saturation, possibly within the so-called instability zone as a result of mechanisms of spontaneous liquefaction or of progressive failure. The landslides in the carbonatic context are debris flows and debris avalanches on moderate to steep slopes. The ridge angle is small. Failure is likely to occur after or nearby full saturation. Liquefaction is a likely process triggered by impacts or by downslope progressive failure. As shown, landslide hazard is very high all over the part of the region that is mantled by volcanic ashes. Especially in the last 20 years after the catastrophic southern event, some structural and non-structural measures are being adopted for risk mitigation. The non-structural measures consist in early warning systems essentially based on weather forecasting. The structural measures often consist of check dams built in mountains, creeks, in order to reduce the kinetic energy of debris flows. A major problem, however, is the size that many landslides can soon reach, making sometimes check dams of little value. In some cases, metallic fences with wire ropes attached to steel posts and anchored to the bedrock have been installed within the pyroclastic covers in areas susceptible to failure, and this in order to prevent slope failure, which might lead to catastrophic landslides. Other mitigation works are large retention basins built along the presumed flow path. The town of Quindici, for instance, has been protected by a retention basin located upslope the urban area. The town of Sarno, too, has been protected by 3 distinct retention basins built just upslope the town. Finally, the right figure in this plan shows the debris flows that took place in the area of the town of Braccigliano during the 1998 Sarno event. The figure on the left shows the areas that are considered to be susceptible to further flows. This slide finally shows 3 retention basins, black in the figure, which should be constructed to protect the town. That's all. I thank you very much.